artificial intelligence has advanced at an unprecedented pace, transforming both research and real-world applications. While innovations in model architectures and training algorithms have been central to this progress, the efficiency of the computational infrastructure that executes them is equally critical. At the core of modern AI systems are GPU kernels, low-level routines that implement fundamental operations like matrix multiplication and convolution. Even modest improvements in GPU kernel efficiency can translate into dramatic reductions in training time, inference latency, and deployment cost, making kernel optimization a cornerstone for sustaining AI's rapid growth. Yet designing and optimizing GPU kernels remains one of the most challenging tasks in high-performance computing. The performance of a kernel depends on subtle interactions between thread scheduling, memory hierarchy utilization, synchronization, and hardware-specific characteristics. Small changes, like adjusting tiling strategies, unrolling loops, or aligning memory accesses, can yield disproportionate improvements or catastrophic slowdowns. As a result, the kernel optimization landscape is highly irregular, architecture-dependent, and difficult to navigate. Historically, kernel optimization has relied on two main approaches: manual tuning by expert engineers, which is effective but labor-intensive and hard to scale, or automated compilers and domain-specific languages like TVM and Triton, which apply heuristics or search, but often struggle with irregular operators and hardware variability. Now the rise of large language models, LLMs, offers a new frontier. Beyond their ability to generate correct code, LLMs can be guided to reason about hardware trade-offs, adapt to profiling feedback, and iteratively refine implementations. But prior work has largely treated LLMs as single-shot code generators or simple refinement tools, underutilizing their potential for structured exploration of the vast, complex design space. We identify three critical limitations in existing methods. First, naive exploration strategies. Most agents refine code linearly, learning only from the immediately preceding attempt. This fails to leverage the rich history of prior trials, often trapping the system in local optima. Second, monolithic agent design. Kernel optimization is multifaceted, requiring planning, implementation, and reflection. Assigning all these tasks to a single, generalist LLM leads to inefficiencies and poor coordination. Third, the planning implementation gap. LLMs frequently devise correct high-level strategies, like apply memory tiling, but fail to translate them into valid CUDA code. This gap stems from the scarcity of expert-level kernel code in training data. To overcome these challenges, we introduce Stark, strategic team of agents for refining kernels. Stark is a novel agentic framework that mimics the workflow of expert engineers through a collaborative multi-agent system, grounded instruction, dynamic context management, and strategic search. Our contributions are threefold. First, a collaborative multi-agent workflow. We decompose optimization into three specialized roles: a plan agent that devises high-level strategies, a code agent that implements them precisely, and a debug agent that repairs failures. This role specialization mirrors real-world engineering teams and overcomes the inefficiencies of monolithic designs. Second, bridging the planning implementation gap. We introduce grounded instruction, a mechanism where the plan agent inserts explicit code span anchors, like improve begin and improve end, to mark exactly where changes should occur. This anchors edits to concrete locations, reduces hallucination, and ensures robust coordination. Third, strategic search for refinement. We frame optimization as a directed search over a persistent tree memory. Each node represents a kernel candidate, and its evaluation, runtime, correctness, compiler diagnostics. At each step, we select a promising node using an adapted epsilon-greedy policy that balances exploration and exploitation, avoiding redundant probes and dead ends. To support this workflow, we employ dynamic context windows, agent-specific views of historical attempts. The plan agent sees its children and top-performing global leaders, enabling reflection and ambition calibration. The code agent accesses not only its own history, but also successful patches from sibling nodes, improving implementation fidelity. The debug agent focuses narrowly on sibling failures, allowing it to fix structural issues efficiently. We evaluate Stark on Kernel Bench, a benchmark specifically designed to assess LLM-based GPU kernel optimization. It includes 3 difficulty levels. Level 1 tasks involve common operators like matrix multiplication. Level 2 tasks require fused kernels with complex data flows. Level 3 tasks are full ML architectures like RaiseNet and LSTM, featuring highly irregular computations. Our results are striking. On Level 1, Stark achieves a perfect 100% success rate and up to a 3.0 times speedup over PyTorch's default eager mode, while baseline agents often generate slower kernels. On Level 2, it maintains full correctness and delivers a 2.7 times speedup, far outpacing reflection, which, despite 100% correctness, runs slower than the baseline. On Level 3, the most challenging tasks, both sampling and reflection agents degrade severely, with success rates dropping and runtimes falling below baseline. Stark, however, continues to produce correct kernels and achieves up to 1.6 times speedup. More importantly, Stark achieves over 10 times speedup compared to baseline agents across all levels. On Level 2, it reaches 16 times speedup over reflection, a dramatic leap in performance. These gains are not just about correctness. They reflect Stark's ability to jointly optimize for both correctness and efficiency. Ablation studies confirm that each component matters. A single-agent model with strategic search performs better than sampling, but not as well as Stark. Similarly, a multi-agent system without strategic search, using best-of-K sampling, improves over baselines, but the full combination yields the largest gains, demonstrating that structured planning and feedback-driven search are key. What makes Stark truly powerful is its ability to reason about hardware trade-offs, learn from failures, and iteratively refine kernels, not just generate code. It doesn't just write faster kernels, it understands why they're faster. This work suggests that LLM-driven agents are not just tools for code generation. They are emerging as autonomous performance engineers. By combining multi-agent collaboration, grounded reasoning, and strategic search, Stark represents a major step toward fully automated, scalable GPU kernel optimization. Looking ahead, we envision extending this framework to broader classes of operators, diverse hardware architectures, and even cross-kernel scheduling decisions. More broadly, Stark points to a future where AI co-designs algorithms and infrastructure, accelerating the entire stack of large-scale computation. The era of autonomous, intelligent system optimization is no longer science fiction. It's here, and it's built on the strategic teamwork of agents, guided by insight, powered by intelligence, and driven by performance.